guys, I'm gonna try to get started like 20 seconds early. I've clocked this talk at about 40 minutes, so if I have time for questions after, we can do that, but if not, you can just find me afterwards. All right, so I'm Josh. All right, this talk is by a plunger before you need a plunger. So what this talk is gonna be about is pretty much how to create a solid architecture and how to get your architecture to a solid place from a point where it's not. All right, so without further ado, let's just jump right into it. Okay, so one of my mentors once told me this exact thing, buy a plunger before you need a plunger. And at the time, I thought it was pretty funny, but it's actually pretty true as well. And the gist here is that you want to make sure that you have a tool to like address your mess before you actually get into the mess. A lot like what the title is saying right now. And this is a lot. This relates a lot to software engineering. I mean, many times we have requests and bugs and features and things like that coming down the pipeline. And we want to make sure our architecture is always at a good place to where we can deliver in a timely manner without having to do like major refactors or a lot of work that may hold up, you know, the actual release date or anything like that. So with that being said, when we think about our architecture, a lot of the same concepts that we use to create good architecture and software, these concepts apply to pretty much anything when it comes to engineering. For example, right? So let's look at this plunger, for example. And obviously, this plunger will be a metaphor for our code base. And there's many different ways to build code bases, right? So likely there's many different ways to build plungers. So we have three pieces to this plunger. You know, we could build the handle and the mouth together and the seal separately, or any different variation that we want, right? One of those variations could be like building this entire plunger, like one 3D printed plunger. Everything is together. And there's benefits to building like this. So if we did want to build this plunger entirely as one piece, this would be beneficial as we know that, you know, all of the parts are made for each other. We don't have to really think about any other possibilities or really consider anything else. We can just build in confidence, as I would say. And there really isn't a lot of guessing here. But the thing here is what happens when like the handle breaks or what happens when the seal breaks? Well, in that case, we have to replace the entire plunger. So when we look at this from a software aspect, this is what we would call coupling inside of, you know, software engineering, where we have two of our components or two pieces of the code base that are coupled together, or they know about each other when they probably shouldn't. They do completely separate things. And, you know, we can't scale this easily at all. Like I said, if one thing breaks in our component, then we have to, you know, refactor or redo that entire component. The same with the plunger. But I would say the worst thing is that we won't be able to replace any of these parts, and we won't be able to fix anything in isolation. So everything will be touching. So it'll have like a cascading domino effect. That's not really too ideal, right? So if we thought about this a little differently, so we have three parts, right? So if we approach this problem in a way where we wanted to compose the parts of the plunger together to make a plunger, that would be a better way to actually approach this. Not only is this easier to see where the concerns are separated, but we can also take full advantage of changing one part while the rest can remain intact. So in code, this may look something like this, where we would have a plunger class, and we would have it take in a handle, a mouth, and a seal, all represented by interfaces. So not only is this scalable since we have a format to replicate a plunger, but it's also flexible because now we can have different implementations of like a handle or a mouth, and it still plug into this plunger and work pretty fine. So this would pass for being scalable and flexible. And in fact, these are two major criteria when it comes to actually building a solid architecture. So there's four that I want to go over today, and these are going to be scalability, flexibility, modularity, and preventability. So for the last one, preventability, it's more, that is more about having your code base in a place where you can actually prevent the problems. But you'll see that preventability usually comes after the first three are usually in place. But first, let's talk about scalability. So when it comes to scalability, right, I've tried to sum these things up into a couple of questions, right? So there's two main questions you want to think about when you are talking about building a scalable code base. And one of them is, how easy is it for your architecture to accommodate more and diverse pieces of code? And the second is going to be, how easy is it for other engineers to understand and modify your code? So when you're thinking about this, you should also think about what is the cost to add a new feature? How much of your architecture is used when you're building out something new? If you have a lot of stubs, that's usually not a good sign. That means you're not utilizing all of your architecture. And how easy is it for other engineers to understand and modify your code? Is your code easy to read? Is it explicit? All of these are going to matter when you're thinking about scaling your code base. And then lastly, what's going to be the ramp-up cost for new engineers? Is it going to take 90 days, or is it going to take more than 90 days for them to actually start contributing? The next one is going to be flexibility. So we can sum everything up with flexibility into one question, which is, how reusable is your code? Some subsequent questions you want to think about with this is, how easy is it for you to use one part of your code that satisfies one criteria for another part of your code that needs that same criteria satisfied, but for a different reason? And then you want to think about, how coupled is your code? And then the opposite of that, how abstracted is it? All of this goes into your code base being flexible. The third one we want to think about here is modularity. So there's two questions here when it comes to trying to make your code base more modular. How compartmentalized are your functional components? And how easy is it for you to make an isolated change? So a modular code base is going to have its core components grouped together logically and composed to create something like a feature or a library, anything like that. And then a module is going to contain all of the classes necessary to make up the module as a whole, obviously, and expose it through a public API. So we can see this concept a lot when using tools like Dagger, and even within Android Studio lately with the module features. And then lastly, we have preventability, right? So with preventability, there's going to be two questions here. And it's going to be, how does your architecture avoid bad usage? And how does your architecture guard the code base? When you're thinking about guarding the code base, you want to consider, how costly are refactors? And also, how dependent is your code on code that's not yours, like third-party libraries and things like that? All right. Okay, so these are 4 criteria that can easily be put together when you have your code base separated in functional layers. These layers usually go by many names in different architectures, but we'll call them the platform, the framework, and the implementation layer. So other than the platform layer, these layers ideally should be platform agnostic, meaning that it has no dependence on the Android SDK to function. And it's easier to think about when it's put like this. So your platform is who you need to serve. Your framework is what needs to be done to serve who you need to serve. And your implementation is how you're going to do what needs to be done to serve who you need to serve. All right, so the framework layer is what I would say is the most important. It's going to be a layer of abstractions and interfaces, and that's how they're going to speak to each other. You know, I like to think of it like a boss, albeit a bad one, that tells you what the result that they want is, but it doesn't tell you, how to get that result. So keep this in mind when you're thinking about scalability and modularity inside of your code base. All right, so when you have this approach and you approach your code base with these things in mind, a lot of the 4 points that we're going to go over is easy to kind of just put together in general. It becomes more clear. All right, so this is great to know when you're starting your code base out or when you're trying to move your code base from a point to where it's not, it doesn't have these 4 traits, and you want them to have these 4 traits. Actually, I think that if we were talking about conversion, that's probably what most of us would be in that situation, right? Converting our code base from not having these traits to having these traits. So let's talk about that for a sec. All right, so before we discuss converting, the purpose here is going to be to provide tips, but keep in mind these tips are going to be centered around, obviously my experience working in teams and things like that, and what I've seen to be the best solution to getting these traits inside of your code base. But as usual, there's more than likely, more than one way to eat this potato, some known and unknown, but I'll show you just one way. So before we even start, again, to note, to be preventative, you want to have your code base in a place where the final that we'll see. You want to have your code base in that place. But that being said, let's look at this scenario. All right, so let's imagine that it's 2021, right? And Tide has become this large tech company. And they realized that they didn't capitalize on everyone who enjoyed eating Tide Pods. So they create an app for that to kind of like enter that market. And we've been hired to look into this app, and we've inherited this code base, all right? So when we take a look at this code base, we see that there's a standard MVP architecture here. It has common usage of tools like Dagger, which is a dependency injection framework, for those who don't know. And it's great that we're utilizing interfaces via contract because this is going to inherently add separation of responsibilities for us. And then, of course, it's going to put us a step closer at our code base being flexible and scalable, all right? So after looking at here, we go and we take a look at an implementation, which is the presenter here. And it's pretty okay. As we can see, they generally seem to be following the rules of MVP, and we can see that the presenter is handling business logic and telling the view what to do, and the view is null, or nullable, as it should be. So for the most part, we can apply this presenter to different parts of the code base as it's intended. All right? And this is pretty much the setup in the app. So we confirm that this applies throughout the entire code base. So we're good to go. All right, so it's Monday, and your product manager comes to you, and they say, hey, we want to add a new feature where users can view this data offline. All right, so the criteria is going to be that we want to allow users to view this screen. It's going to be a new screen, but we don't want to detect whether the user is online or offline in real time. We just want to do it when the user enters the screen. So we have a couple of different options here. So when we go to look at the code, trying to think about scalability and flexibility, all right, our first option here is to add this functionality to the view. But remembering our MVP rules, our view should be dumb, but now it knows it's online or offline. And then not only that, but we have to add more functions to our presenter, which can be slightly confusing to any engineer coming after us. Ideally, the view should ask the presenter what to do, and the presenter should just produce it. But now the view knows that the presenter can fetch locally and non-locally. And lastly, we can't really reuse this logic at all. So this really would fail the flexibility criteria. So I think we can aim a little bit higher with our solution. So our next option here, obviously, is to go to the presenter. All right, and this is pretty fair game. But the flaw here is that now our presenter has a bit of logic in it, like a good bit of logic in it. And not only that, but now we have a bit of duplication inside of our presenter, as we can see. So now when we want to add another aspect to our networking logic, we have to put this inside of our presenter, making the networking logic less reusable than it already is. So what we need to do is we need the presenter to just handle managing the view and telling the view what to do. So we want the presenter to make a request to get data, and we need a tool for that. So this tool is commonly called the interactor, so we'll call it that. And what the interactor mainly serves to do is to communicate with the data source and the presenter. And it'll make our code a lot more compartmentalized and cleaner by providing one output for the presenter. And it'll also serve as an abstraction for the presenter. So simply put, the interactor, it makes it so that the presenter doesn't have to know about where it's getting its data. So this would mean that we can make underlying changes to how we're fetching the flavors without the presenter actually knowing anything about it or having to make any changes to the presenter at all. All right, so this sounds great. So how would this look? All right, so we can see here what we would need to do is to create two separate interactors, one for online, one for offline. And we can now only inject the dependencies that we need, which could save us precious performance time. And then lastly, all of the code in our interactor is used, unlike before, which is pretty great. And then now we can go to our Dagger module provisions, or it's pretty similar with other dependency injection frameworks. And we can just pass through our API manager, our local storage manager, and then, of course, the Boolean detecting whether the app is online or offline. And we can simply provide the appropriate interactor for that. So this works because we are representing our interactor with an interface, and our presenter doesn't necessarily care about the implementation, only that our implementation complies with the interactor interface. So this is nice and simple. And then lastly, we can go to our presenter, And we can minify our code now a bit. Now the presenter only cares about its responsibility of requesting data and telling the view what to do as we want it. And the essential statement here that the presenter is saying is, I need to fetch flavors, give it to me. I don't care where you get it from, I don't care how you do it, I just want flavors. And as we can see, with this setup, adding offline capabilities is as simple as introducing another interactor to the code base. So this would be very flexible. All right, so that's great work. All right, and the following Tuesday, we go to check our crash reporting, and we see that there's a bug happening specifically with offline viewing. And it's weird because it seems that there's a button that's not responding to an on-click event, and this doesn't happen online. So we have a one-off bug here. All right, so when we go to investigate, our investigation brings us to our presenter function here, and we look through the code, and we see that a field that should be true is instead returning false when in offline mode. And this is strange, of course, because this works when the app is online. So the next thing we probably want to do is go and look at the interactor that we just created. And when we take a look at this, everything seems expected, or as expected at face value. We're using local storage manager to make a request to fetch flavors from the cache, and we're passing an error back if we get an error, and then we are returning the flavors when we get the success. But we are doing one thing before we return those flavors, which is converting to flavors. So when we look at this, we remember, right, that when we actually created the offline interactor and the online interactor, we duplicated the code that was inside of it. And part of this duplication was this convert to flavors function. So when we decide to take a deeper look into this convert to flavors function, we see an obvious mistake here. So it seems like we forgot to completely copy the item URL building. So this is going to break don't repeat yourself anyways, but business logic like this should be testable, explicit, and readable, of course, and reusable as well. And likely, whenever we need to convert a response to a flavor, we're going to need to reuse this logic as well. So we need a tool to be able to encapsulate this logic. So this tool goes by many different names in different architectures. Some call it a reducer, but for this, we'll call it a transformer, all right? So before even going into what the transformer will do, which is pretty obvious, business logic is very important, and it should be testable. So unless you are providing your response object directly into your code base, you'll always have a need to turn an object from one thing into something else. In this case, from a response to flavors. And this is exactly what the transformer will do. It'll hold that logic that turns a response into flavors. So what we'll do here is we'll create a flavor transformer, and we'll represent it with an interface that only defines that it's going to turn a response into a flavor. And this would work because our interface definition also allows us to utilize this in list form, which we'll be returning, as we saw before. And then lastly, what we can do is we can copy over the contents of convert to flavor function over into our transform function. All right, so now when we go back to our two interactors, we can see here that all we have to do is extract out that logic, and we only need to define what type of transformer we need. In this case, a transformer that turns a response into flavors. Remember, everything inside of the constructor is our interfaces. It's our framework layer, and we are looking at an implementation right now. So we are defining what, not how. So since both interactors have the same needs, we define the transformer, or we define that the transformer needs to be able to handle handling a response and turning it into a flavor. And then lastly, what we can do is we can replace our convert to flavors function with our transformers transform function, as we can see here. Then we'll go to our Dagger modules provisions and define a transformer to provide, in this case, flavor transformer. And then we can retain functionality elsewhere and fix our bug as well, now that the logic is the same. So this would set us up for success both now and in the future. Okay, so real quickly, let's recap. We have our view for handling platform work. We have our presenter for managing the view and the data. We have the interactor to interact between the presenter and the data layer. And we have our transformer to specifically handle transforming or parsing responses with business logic. All right, so far so good. We now have steps that we can take to create new features and create isolated logic that can be scalable and flexible. All right. So The good work is also reflecting inside of our reviews. Reviews are soaring right now, actually, and people really can't get enough of the good work. So we see, though, that there's one consistent complaint, and it's that users seem to hate our flavor grouping feature, instead wanting to get to their flavors quickly in a single ungrouped list. So next sprint, your product manager wants you to add a feature where users can view this data in a single ungrouped list, okay? So now that we have this set up, let's put our architecture to the test. All right, so firstly, this is what would define whether a view displays as grouped or not in our architecture, all right? We have an interface flavor, and then we have two objects that are implementing this flavor interface, single flavor and grouped flavor. And then somewhere down the line, we have this when statement that determines whether the view should display a single or a grouped list. And then next, this is the current version of our flavor transformer here, which determines if a flavor is grouped or single. So we can see here that the condition that's being checked is this children is not empty, then we're returning a group flavor, and then a single if that case is not true. And this would plug into the rest of our architecture, which only requires that a response is turned into some kind of flavor. So what would this mean? Okay, so again, because our framework layer is completely of abstractions, the rest of our architecture doesn't necessarily have to care about what we do under the hood. It just needs to adhere to the contract to work. So everything from our interactor, our presenter, and our view, in this case our fragment, won't need to change at all and doesn't care about it. So what we'll do here is we'll define a new transformer since we always want the single flavor to be shown in this case. And we'll call it single flavor transformer. And what we'll do is we'll do the same thing that we did for the flavors transformer, which is represent it with a transformer interface, response to flavors, we transform, and then we always return a single flavor in this case. And then next what we'll do is we'll create a new module for this new screen, and then we'll define the transformer we want the module to use. So since the code in our original flavors architecture is reusable, all we need to do is provide a new transformer to tell the rest of the architecture to use. In this case, our single flavor transformer, because that will turn everything to a single flavor to display as a flat list. And then now all we have to do is just put the pieces together. So the way that we'll do that is we'll go to our component, which would define the dependencies for the new single flavor screen. And as you can see here, we can reuse some of the logic that we already created in the original architecture. So this TidePod flavors module, it would contain the presenters and the interactors and things like that. And then our data module would include mappers and transformers and everything that's related to data. So all we have to do here is simply replace the data module, and then we still use the original flavors module, which includes the presenter and the interactors and things like that. And this would allow us to plug single flavors transformer into the rest of our architecture so that's compatible. And then there's one more step that we have to do, which is telling the architecture which transformer to use by creating a new component. All right, so all we have to do here is subclass TidePod flavors fragment. We'll override the component that was a variable inside of that fragment, and then we'll build this new component which utilizes the single flavors transformer, and then we have our feature. All right, and this is an example of having a modular code base. So we have a skeleton for our architecture to be replicated, making it scalable. We successfully shared our components, making it flexible. All right, and we can make isolated changes to modules and plug it into the architecture safely and cleanly, making it modular. So because our dependencies were modularized, we are able to pull out the part we want to change and plug in the part that we actually want while retaining functionality elsewhere. So how can we be preventative? All right, so the more we apply these concepts, the more preventative we're going to be. So it's going to automatically decrease coupling, and it's going to allow for testing to be easier as well. These principles can be applied to any architecture, not just MVP, and we have a strong skeleton now. So this is good, but the hard part, or the part that has the most work, is maintaining and making sure that your code base stays this way. So that being said, here's a couple takeaways that are going to go over some preventative measures that you can take today to make sure that your code base is on guard. All right, so the first here is going to be wrapping your dependencies. So not wrapping your dependencies and instead exposing it to your code base puts you at the whim of the third party's code base. So this also increases modularity in your code base as each dependency can be incorporated within its own module. And then the next is going to be maintaining clear separation of platform versus core architecture. All right, so unless you're using Android architecture components, you never really want your Android SDK components to be a main part of your architecture, like context and things like that. And this is also going to be good for modularity and scalability as it is going to lessen your dependence on the ever-changing platform, as we kind of saw in the keynote today. So that being said, the last one that we want to take note of is naming your functions. So this is going to be a very simple one, but it's often overlooked as well. But each accurate and informative name we can give our classes and functions is an investment into our code base. So that being said, let's talk about what is probably the most important of these three, which is wrapping your dependencies. So at some point, you're going to eventually need to lean on others to help your product in your code base. So when we're thinking modularly, we always want our components to be represented and used through its interface and not its implementation. So whenever we're integrating a new library into the code base, just make sure that you're wrapping it with an interface to protect yourself against changes from the library. All right, so there's two main benefits we're going to get from this. The first is going to be a clear separation of concerns, and then the second is going to be protection from the third party's code base itself. So to illustrate the first, all right, let's go back to our example. Let's imagine that product decides that it's time to switch analytics providers, let's say from Adobe to Firebase. And here's an example of how it's being used in the code base. So it's being used in one of these presenters, and aside from the repetition, this isn't really ideal as this is coupled to our analytics implementation logic from another implementation, the presenter in this case. So when we have to switch this out, we now have to find all of its usages and change it everywhere. So since we didn't wrap our dependencies, we now have to prepare for like a major refactor, and it's going to touch many, many, many different files. So a better way to do this could be like this, right? So we'll represent our analytics needs with an interface. Let's call it analytics provider in this case. And when we're thinking about our layers, our platform, our framework, and our implementation layer, we can look at this set of abstractions as a set of statements. So before we were saying inside of our presenter, when this give a Tide Pod submit button callback is triggered, send this data to Adobe Analytics with this key and this context data. And this is way too detailed for our presenter to know. But now what we're doing is we're instead saying, hey, when this give a Tide Pod submit button callback is triggered, send this data to our analytics provider, whoever that is. And this is great because the implementation is hidden. And when we call our analytics provider, it could be our old, which is Adobe, or our new, in this case, which would be Firebase, without making any changes to the rest of our core architecture. So this would mean that we can switch from our old provider implementation to our new provider implementation without having to change any other part of our code base. And ultimately, this is a great preventative measure that you can take to wrap your dependencies. So as I mentioned, this is not the only benefit that we get from this. We also have protection against any changes that the library makes to its API. Again, because our code base doesn't necessarily care about implementation of function, rather than this change that we're seeing here happening everywhere inside of our code base, it's going to be contained in one class or one module. And this modularization is a good preventative measure, which helps us switch out parts without affecting the rest of the code base. And this clear separation that we're seeing right here, this also applies to the next preventative measure that you can take when thinking about your project structure. So as I mentioned before, a solid architecture is one that is platform agnostic. So your business logic shouldn't and likely doesn't need to depend on Android or your platform to do what it needs to do. So when we're creating a platform agnostic architecture, we're automatically decoupling our code from the platform, making our logic easy to test. And this is going to protect us from our platform, or in this case, Android updates. And it'll allow us to only have to manage the more stable and more consistent language updates, in this case, Java or Kotlin. All right, so there are some things, though, that the platform makes easy for us, which would render implementing a more native approach obsolete. Or perhaps the platform, just makes our code easier to read and more straightforward by utilizing some of its components. So while, yes, we should avoid coupling our core architecture with Android SDK components, there are times where that could be beneficial. And there is a way to integrate Android SDK components into your core architecture without breaking these rules. So here's a common scenario here, parsing JSON data, in this case from a file. So there's two ways to parse JSON data in a file. There's one way is using the Android context, and then the other is using a set of streams to kind of get that data from the file in a more Java-esque way. In this case, Android makes it easy for us to do what we need to do, so there's really no need to reinvent the wheel here. We can just use context. The core operation we want to do is read a file's contents into a string, so we can just simply abstract that out into an interface, as we can see here, in this case, file reader. And then we'll create our JSON file reader, which utilizes context to open the file. But the thing here is that this is not a good implementation, because now our framework layer inherently knows about the Android API and the raw resource ID, causing all others in our core architecture to have to know about that as well. So instead of incorporating Android SDK components like this, what we can do instead is just replace our raw ID parameter with something a little less coupled with the Android SDK. In this case, a string parameter only designating the file name, since every implementation of this file reader would need to have the file name anyways. And this would make it a lot more compatible with different ways to do that. So since this reader depends on context, now we need a way to define this context dependency inside of our code base while also not coupling our code with Android SDK components. So when we're thinking about maintaining clear separation, an easy way to do this is to explicitly define your platform module. So your platform module is going to provide all of your Android dependencies, context, resources, all of that. And this also forces you to explicitly state that your module depends on Android somewhere. And in this case, it depends on context for the JSON file reader. So in addition to this, we can further structure our project to reflect this as well a bit more. All right, so if any of your implementation components depend on Android, like our JSON file reader, you can take an extra measure, or you can do it as an alternative, and you can package them inside of an Android package to help create a clear indicator that this implementation depends on Android. Or what you can do is you can prefix your class name with Android to further support this separation if you find that necessary. But what I would say is that naming is probably, it's more important than what it comes off, especially when it comes to having a good scalable and preventative architecture. So when it comes to naming, right, so we often joke as software engineers that a lot of our productivity goes towards like trying to find the right variable and class name and things like that. And this is funny and stuff, and it's an exaggeration, but there still is a lot of importance into making sure that your functions have good naming conventions. And ultimately, what you want is you want your function names to be readable and explicit, while also considering flexibility and scalability and different ways that it can be used. So we can inherently couple two parts of our code base just by choosing bad naming conventions for our architecture. So here's an example of how this could look. All right, so in this scenario, we have some favoriting functionality between the view and the presenter. So this is bad because on favorited heart clicked knows that the UI is utilizing a heart. And then on show favorite snack bar, right, at the very least, we know that the platform has snack bar capabilities. And at the most, we know that the platform is Android. So this is coupling both our UI and our platform to our architecture, which isn't good when we're thinking about being platform agnostic and things like that. So a way to fix this would be to remove any indication of the platform or the UI in these components. So it's very simple. Now we have on favorited, which knows nothing about a snack bar, and then we have on favorite clicked, which knows nothing about a heart. So not only does this make our architecture a little bit more platform agnostic, but it also makes it a bit more reusable because now the underlying UI can change and the architecture can still make sense. So this is really good as a preventative measure, all right? Okay, so we went over a lot. With all of this in mind and incorporated when things hit the fan, we now have a plunger to be able to get us out of it. And I've stepped through the code base and the reasoning of like creating a code base this way, just utilizing MVP as an example. It doesn't have to be MVP, just to kind of show like why decisions like this are made or should be made. But again, the purpose here is to start off or to get your code base in a place like this to where you can really benefit from the preventative measures that these aspects will make your code base. So if you start here, it becomes increasingly more likely that any change coming from product can be handled by any engineer. And they can just pick up where you left off, piecing things together, replacing things, just pushing the architecture forward. So all of this because you had a plunger before you needed one. All right, so that's it. I'm Josh, and I'll be around for questions or whatnot if you guys have any.